Okay, so let's see where we can use this in some practical examples. So I just thought we'd cover a few of these. So first of all, let's do this one, example 5. So we have a fluid which is flowing through across this plane surface. Okay, so here's the plane. This is the normal to the plane, and this is the fluid, or the flow of the fluid. So a fluid is flowing across the plane surface with uniform velocity. So it means the velocity is not changing and it's the same everywhere in the plane. If n is the unit vector perpendicular to the plane, it's this n, let's find the volume of the fluid that passes through a unit area of the plane in a unit time. So we're going to say like unit area might be 1 by 1 and a unit time might be 1 second, or it depends on the units. But okay, so first imagine 1 unit of time has elapsed. So here's the picture. Then over a unit area, this is the area of the plane, the fluid will have filled a box. Here, we'll fill this box. The box may be represented by a parallel pipette, this shape here. The volume we seek is the volume of this parallel pipette. And the volume of a parallel pipette is, so that's in the 1 unit of time, that's how much water or fluid will have passed through. So the volume of a parallel pipette is this area here times the height here, this height here. That's how you get the volume of a parallel pipette. The area of the base is 1 unit, that's what we said, 1 by 1. The height is given by the projection, the magnitude of the projection of V onto n. So in other words, here's the n. So I want to know this height. We want to know this height. So it's this V projected onto here. So that's the height. So that's what we want. We want the height. And from Formula 5, for the expression of the projection, it looks like this. But we recognize, that n this is a unit vector. So this part is just one, basically, n dot n is this thing, which is just 1. So we just have n dot v n. So this is, so the magnitude of this is the magnitude of this, and that is the absolute value of this times the magnitude of this by part 1 of proposition 3.4. Okay, I don't have that in front of me, but so we now have the height. So all we needed was the height times the area, the base area, which was 1. So it's just the height. So that is the volume. Okay, now we're going to do 2 other kind of nice proofs using vectors. It says, we conclude this section with 2 illustrations of how wonderfully well vectors are suited to provide elegant proofs of geometric results. So here's a geometric result that we might have learned in high school. This is an arbitrary triangle. We want to show that if you take a midpoint of this side and a midpoint of this side and connect them, that will be parallel to this, and the length of this will be half of the length of this. So we're going to redraw this with vectors like this. So we're going to have a vector here, am1 and am2, and this whole vector is called AC, and this one is called AB, and this is called BC, and this is called M1, M2, displacement vectors. So we want to show 2 things. One is that the midpoint, both are, that we want to show that AM1 equals, where's A? This equals 1/2. I'm sorry, that's not, these are, right, the fact that this is a midpoint means that AM1 is half of AB. And the fact that this is a midpoint means that AM2 is half of AC. So we have those. So then M1, M2 is equal to AM2 minus AM1. AM2 minus AM1 gives us this one. That's the one I always get confused with, but that's true. And AM2 and AM1 can be written in, we just said, here AM1 can be written like this, and AM2 can be written like this, and that's what they wrote here. Then we can factor out the half, and we get AC minus AB, which is just BC, right? AC minus AB is BC, so we get that here. And they said, but now we've shown that this, which is this one here, is 1/2 of the bottom one, BC. But that means that they're parallel, right? To say that this is a scalar multiple of this means that they're parallel. So the two vectors are parallel. And also from part 1 of proposition 3.4, we have that the magnitude of this equal, well, let's see, where are we? The magnitude of this equals half, or we're doing it here. So the magnitude of this equals the magnitude of this, but we can factor out the 1/2. So we get the magnitude of this is 1/2 the magnitude of that. That was the other thing we wanted to show. Okay, that was a nice proof of the fact that this is half the length of this, and these two are parallel. So we used vector geometry to do that. Okay, and the last one is show that every angle inscribed in a semicircle, so here's an angle inscribed, is a right angle. How can we do that? So we're going to redraw this picture. We're going to say here's the center. This is a radius A, radius B. So A and B are the same length. And this here is A minus B. And this one, this is minus A. So if this is the axis, then if this is A, we can call this minus A. So this is minus A minus B is here. Okay, so we have that. All right, now, so what we want to show is that this is perpendicular to this. But that means we want to show that their dot product is 0. Right? If the dot product is 0, then they're perpendicular. So we need only show that A minus B is perpendicular to this, which means that their dot product is 0. So we take this times that, we can factor out 1 out of here. We get A plus B. And then we look at these properties here, properties of dot products. So we have this one, and this one, and so on. We look at those, and we can do a distributive law. So take this times that plus this times that, which is what they have here, and then do it again. Take this times that and this times that, subtract them, and so on. We get this one. Then we get this term, and this term cancel out. So we just get this and this. But these, this is the magnitude of A and the magnitude of B, but these are both radii, so they have the same magnitude. So we get 0. So that means that these two were perpendicular, which is what we wanted to show. Okay, so that was also a nice proof. Okay, so some of these exercises, A and B, they want us to compute A dot B and this, and this. So just A dot B is easy, and the magnitude of A is the square root of A dot itself, and the magnitude of B is the square root of B dot itself. And the same with all of these. Okay, find the angle between each pair of vectors. So let's just quickly. So we're going to use this formula here, and we have vectors, so we just do the dot product of the two vectors, and the magnitudes, we have to take the dot product of each times itself and take the square roots, and we get the magnitudes here, and we have to take the inverse cosine of that, and that will give you the angle. So you can do that for those. Okay, for the projection of B onto A, that is, you just use the formula. They want you to calculate the vector, not just the magnitude, but the vector, the projection of B onto A as a vector. They didn't say magnitude of this. Okay. Here's another one. Give a unit vector that points in the same direction as this vector. So you just have to create a unit vector, which means you take this divided by its magnitude. To get its magnitude, again, you just take this dot itself and then the square root, and then you divide each term by that, and that will give you a unit vector in the same length, because it'll be a scalar multiple of this. Sorry, in the same direction. Okay, the next topic is the cross product, and the cross product is different than the dot product. The dot product, remember, was also called the scalar product because it resulted in a scalar number, but the cross product gives you a vector, so they call it an honest product, because you take two vectors and you get a new vector. So they said that when we defined the dot product and vector addition and so on, we defined them all algebraically. We didn't define them in terms of thinking of the pictures of them. We just said how to add vectors. We just said element by element. We hadn't even introduced the idea of the picture yet. But here we're going to talk about the cross product first geometrically, and then we'll deduce algebraic formulas for this cross product. So this is a little bit hard to talk about without doing a demonstration with one's hand, but if you do the right hand rule, so if this is the right hand of somebody, if you did the left hand and did the same thing that we're going to say to do here, your thumb would actually point down. So in other words, if I want to know what A cross B is, I take my right hand and I what do? I point it in the direction of A, and then I rotate my fingers, or A, towards B, and then the cross product is going to be a new vector, and what we're trying to figure out here is what direction does it point, and it's always going to be perpendicular to the plane AB, but there are two directions it could be. It could be up or it could be down, and if I use the right hand to do that, then my thumb is pointing up, so that's the direction of A cross B. Now if you used your left hand and you had to go from A to B with your fingers, your thumb would have to point down, but we're not using left hand, we're using the right hand. So this is what we're defining this thing called the cross product, and one thing we need to know about it is what direction is it, and this tells us what direction it is. The other thing, of course, we need to know is how big it is, how long it is, what its magnitude is. And that is given by this formula. So the magnitude, the symbol for the cross product is x instead of dot. And so the magnitude of this is given by the magnitude of A, the magnitude of B, the sine of theta. Now, if you remember, the dot product was the magnitude of A, magnitude of B, and the cosine of theta. So this is different. This is the sine of theta. So remember that the sine is 0 when theta is 0. The cosine was the opposite. The cosine was 0 when theta was 90 degrees. But the sine is 0. So when is this magnitude going to be 0? When the two vectors are in the same direction. The angle between them is 0, means that they're in the same direction. Okay? So that was the opposite of the dot product. The dot product was 0 when they were perpendicular. This one is 0 when they are in parallel, when they're in the same direction. But this one again is not, that's just the magnitude of this one, but the vector direction is what we described here. The magnitude is given by this here. Let's read what they say. Let A and B be two vectors in R3, not R2. So the cross product is not defined in R2. The cross product or vector product of A and B, denoted by A cross B, is the vector whose length and direction are given as follows. So we need the length and the direction for this. So the length of A cross B is the area of the parallelogram spanned by A and B. So it's this thing here, A, B, it's going to be this area. Or is 0 if A is parallel to B, or if A or B is 0. Anyway, those are just weird cases. Alternatively, the following formula holds. So this formula gives you the same thing as the area of this thing. So you can check that out, I guess, where theta is the angle between the two. Okay, the other part is the direction of A cross B is such that A cross B is perpendicular to both A and B, but that doesn't tell us everything, because it could be this way or it could be down when both A and B are non-zero, and is taken to so that the ordered triple A, comma B, comma A cross B, so A is a vector, B is a vector, and A cross B is a vector, is a right-handed set of vectors, as shown in this figure. So anyway, I guess I'm not sure what that means, but we already said that. By saying that A is right-handed, by saying that this is right-handed, we mean that if you let the fingers of your right hand curl from A, you have to remember this part, from A towards B, then your thumb will point in the direction of A cross B. Okay, so that is the definition of the cross product. So they say, okay, let's figure out the cross product of IJ. So you take your hand like this, put it at I, and fold it towards J. Then you're going to go up here. It's going to be in the direction of K, actually. Now, what's the magnitude going to be? It's going to be the magnitude of I, the magnitude of J. Those are both 1, though, and the sine of the angle between them is 1. So the magnitude is going to be 1. So it's going to be in the J direction, and in the K direction, and it's going to be magnitude 1, means it's going to be K. So this gives us that I cross J equals K. And you can do the same kind of thing to show that J cross K equals I, and K cross I equals J. Okay? So we can do the same thing for these. And they say you can use the circle sort of to remember. So if you do I, J, you get K. If you do J, K, you get I, and so on. And also, if you go the other way, you're going to get minus. So you do I cross K, I cross J gives you K, but if you do I cross K, you'll get minus J. Okay, what else? We have the properties of the cross product. So the first one is important, that A cross B is not the same thing as B cross A. So it's not commutative, right? Because they don't even, they won't even point in the same direction, right? We said that you have to fold your hands in a different direction, you're going to point in a different direction. So they are not even pointing in the same direction, so they are not the same thing.